All right, we're live to tape. Good day again, everybody, and welcome to our Monday plenary. So, this week we're going to tackle a very interesting and relevant thinker who, strictly speaking, wasn't a philosopher, but he was just about everything else you could imagine: a mathematician, a logician, really the father of contemporary artificial intelligence, more or less one of the key inventors of digital computing, and certainly the one who's credited, I think, rightly with having formalized the universal definition of a digital computer. His name is Alan Turing, Cambridge based for most of his life. And he's well known for about three different things. So well known, in fact, that Hollywood eventually got around to making a movie about him, and maybe some of you have seen that. Has anyone seen The Imitation Game? I think that was the name of the movie. Has anybody seen that? Nobody?
No.
No? Okay, not yet. All right. Well, given what we're going to say this morning, somebody saw it. Naomi, you saw the movie. Did you enjoy it? Was it interesting for you? Yes, no, maybe? Well, I haven't seen it myself, but I've been told that it's not too bad. Yeah, interesting. Okay, well that's good. I'll just put the title in if anyone else is interested in having a look at it. I think that Turing himself is fascinating in terms of the thesis he's proposing to us, and I think that Hollywood, by all accounts, did a reasonable job with him, and they focused on the issue that we're going to discuss this morning, namely the what has come to be called the imitation game, or in a slightly more formal context, if you want to use the terminology that we're going to adopt, it's the Turing test, named after him, of course. So let me just preface this. I'll give you a little bit of background about Turing. He actually became secretly famous during World War II by being put in charge of a top secret group that had been convened by the British government to break the code that the Nazis were using to transmit their military orders and other strategic information. So this code was deemed by them to be so sophisticated that it was basically unbreakable. So they were broadcasting the code in the clear. Of course, it didn't do you any good to pick up the coded messages if you couldn't decode them. And probably we all know today a little bit less naively, I think, that every code in principle is breakable. It's only a matter of time. But they were very confident about the way in which this code was devised. So the British put together a team, a very eclectic bunch of people, led by Turing, who was already a well-known logician and mathematician. But they put together people who were good at solving crossword puzzles and other kinds of puzzles and language games and different kinds of gifts. And they assembled them all, and they did manage to crack this code. It was called the Enigma Code, enigma meaning mystery. They did manage to crack the code eventually, but of course Turing could not have been made famous for that immediately, because they didn't want, obviously in wartime, you don't want the enemy to know you've cracked their code, then they'll stop transmitting in it. So this was advantageous for the Allies, but Turing remained under wraps, obviously, for the duration of the war. And then later he was justly credited with having led that team. But, that was a very particular kind of episode in history, and it showed perhaps a flash of his brilliance and the people who helped him. But he really devoted most of his energies to developing a model for digital computers. So we're looking at the Turing test, which is of interest to our discussion. But if any of you are in computer science or logic or mathematics, if you're doing any of those subjects, then you may be more interested in the universal Turing machine, which is the other thing that he's credited with. And I'll just type that into the chat room. the Universal Turing Machine, or UTM as it's known, is really a model for all digital computers. So Turing is not the inventor of the digital computer per se, because that's an ongoing business, and it depends with every generation on the technologies being used. We've been through several generations of technologies, but the actual model of the Universal Turing Machine is a model for all digital computers. So that is the generalized credit that goes to him. All digital computers, anything that you're using, be it a cell phone, or be it a desktop computer, or be it some other kind of supercomputer, as long as it's digital and not analog, then it's going to be captured by Turing's model. And basically, a machine of this kind has, as some of you may know, three basic sorts of facets to its operation. One of them is an input. Every computer needs input to run on. It's fuel for the engine. But then there's also an internal state to the machine. So dependent on the input and the state that the machine is in when it receives the input, it will then do whatever it's programmed to do and produce an output, and so forth. And that's the cycle. So maybe some of you now already see the relevance to our discussions of Descartes and Berkeley and Churchland, because Turing's question in this very famous reading that we're looking at today, published 71 years ago, is really, can a machine think? So we already know from Descartes that thinking is, by him, deemed to be a mental activity. He's a dualist, so he thinks there's a physical world, but he's not too sure about the composite matter, as you understood from his meditations. He's much more certain that he can think, but that's a mental activity for him, not a physical one. And then Berkeley tells us that in fact Descartes is right about that, but not about the physical world, because there is no physical world independent of a perceiving mind, right? So for Berkeley, who's the idealist, we have only a kind of monism. The only things that exist are perceiving minds. And then we looked last week at a rebuttal of that, really, by Churchland, who's a materialist, and he's saying no. Minds are not things. They're just a word we use because we don't really know how brains work. So we talk about the human mind or any other kind of mind, but ultimately, as you know from Churchland's materialism, which is called eliminativist because he wants to eliminate these very foggy terms that we use on a daily basis without really knowing what they mean. Churchland hopes, and he's not alone in this, that at some point neuroscience is going to become mature enough to be able to explain to us in terms of physics and chemistry and biology exactly how the brain works. And if that comes to pass, we will know what it means to be thinking. And it will not be Cartesian language, it will be the language of the physical brain. That's going to inform us not only what we're thinking, but why we're thinking it, and how thoughts come to spring into what we call our minds. So for a reductionist, a materialist like Churchland, it's all a function of the brain. So Turing is going to take a different tack, because he, not being a philosopher, can afford to avoid this debate, which is really an ontological debate about the nature of brain or the nature of mind, yeah? But Turing is going to take a position that's quite different and almost unique in a sense. And that position is called functionalism. And I'll just put that word in and then give you a very quick characterization of why it's different. And this is easy to understand, although you may have not seen the terminology before. Functionalism is full-blown a fairly complicated set of kinds of arguments about the nature of certain things, but for Turing, and in his case and in our case, it's not complicated. I'll give you a very basic conception. What Turing is saying is that he doesn't need to answer the question of whether minds are thinking or brains are thinking, because if we can build a computer that can imitate the human being well enough in terms of being able to carry on a conversation, then we don't need to know what thoughts are made of, whether they're mind stuff or brain stuff, because we will have built something that actually can fulfill the same function as a mind or a brain, and it's just going to use a different structure to do so. So this version of functionalism that I'm introducing today, and which is really Turing's version, is asserting that, in general terms, a given function might well be accomplished by very many structures which are not at all similar to each other. And yet they may, each in its own way, be able to achieve a certain function. A very simple example of that would be flying. Well, simple these days, not so simple perhaps a few hundred years ago. But let me just ask you to start naming things that fly. If I ask you to start naming entities, be they natural or artificial, what kinds of things fly? Birds, right? And we know that birds in themselves vary greatly, yes? In the way that their wings are designed or evolved. Not every bird has exactly the same genetic set of wings. They're different, right? Planes, exactly. When we come to planes, Jeremy, we see all kinds of planes, be they powered by propellers, right? Internal combustion engines with propellers stuck on them. What the Wright brothers used to get off the ground was like a sewing machine engine, not even, with the propellers stuck on it, and that evolved. Do we have jets? And we have other kinds of things. Kites, yes. Kites could be said to fly, although they're tethered. They still, in a certain sense, we have a saying in English, go fly a kite. So I guess, kites fly. Some insects, yes. All beetles fly. Some insects do. The members of whatever the beetles are, a family or an order, they all fly. That's correct. But again, they don't all fly the same way. Anything else spring to mind? I want you to get your neurons firing this morning. We haven't by any means exhausted the possibility of naming flying things or different groups of flying things. You've got most of them, but there's still a few. Yeah, helicopters. That's right, Jeremy. Helicopters. Leonardo da Vinci actually designed, I think, the first prototype, although the technology was very far removed. Yeah, but helicopters certainly fly in a totally different way. Yeah. Bats, that's right. There are mammals that fly, bats being quite well known.
What about risks, Lou?
What about, who else? What's that, Ron?
Risks, flight risk.
Well, we're speaking literally this morning. Bees, yeah, bees fly, and also drones, right? We have a big industry now of drones, and so those are flying things. Now, the point is that they're all performing the function of flying, right? Better or worse or differently, but they all have different structures. All these different groups of things we've named structurally don't resemble each other, but all of them are able to perform the function of flying. So you see how that ties back into our philosophical question about whether minds are doing the thinking or brains are doing the thinking, or whether they're two different names for the same thing or not. So you have the possibility of different structures, because surely now if we try to apply that concept of structure, we will come up with a brain structure which probably looks nothing like a mind structure, which probably looks nothing like the structure of a digital computer. And yet it's possible that you could have a conversation, some kind of coherent conversation with any of those different structures, if indeed they're able to perform that function of conversing with a natural language. So that's where Turing wants to head. And in focusing his treatment on digital computers, he's concerned only to build or to imagine, because in 1950 they didn't have such a device, but he wants to build or conceive of building a digital computer that could have an ordinary conversation with you. And if you were, on the imitation game as he conceived it, and we'll go to the text in a moment, the imitation game is set up in such a way that you imagine you're in a room and you have two keyboards, and one keyboard is hooked to another to a computer. So if you type in a statement, the computer returns a statement to your monitor. You say good morning, it says good morning back to you. And your other keyboard is hooked into a person at the other end, and that person can type or text with you also. So imagine you're texting with two different entities, but you don't know which is the computer or which is the person. And if, Turing supposes, if we get good enough at building digital computers at some point, you won't easily be able to tell the difference between the person and the computer just by texting with them. And if that is attained technologically, we will have reached a point at which we would definitely be able to assert that a machine can think, at least as well as a human being. So he predicted this in 1950, and he thought in 1950 that it was only a question of storage capacity, that once we got large enough memory capacity into a machine, then somehow a lot of other things would follow from that, including its ability to manipulate the tokens of natural language. It turns out not to be that simple. And that begs some other philosophical questions as well. Why isn't it that simple? But we'll get there today. The main thing is that we want to look at Turing's original argument. Now, some of you may be thinking already, and if so, correctly, that we have certainly by now advanced enough in our understanding of computer science and technology to build machines that can do things a lot better than some human beings can do. Would anyone like to venture an example of a task, if you like, or something that a computer can do, a contemporary machine can do, better than a human being? Does anything spring to mind? Anyone at all? Memory.
I was thinking on like telling time, like how you'd rather just have it like a clock than like a digital clock, possibly.
Well, sure. I mean, some people have a pretty good sense of time, but, we've always had, I mean, this is really a little off the topic because we've always used devices to tell the time, be they sundials or hourglasses or primitive kinds of watches. So, we've always needed some help if we want to track the time. We've always used some kind of a device to help us do that. What about, well, somebody's saying memory. Sure. Computers nowadays, I mean, if you're storing data on the cloud, you probably have access to a lot more data than you do in your immediate memory. That's for sure. Somebody said computation, and I think that's absolutely right. We have computing power now more than we've ever had in terms of doing very complicated mathematical things and computational things that nobody can possibly do. Although, once again, there are interesting counterexamples because there are what we call idiosavant. You know the term idiosavant? Someone who's born with a gift to do one specific thing and they don't even know how they got this gift, but they're really brilliant at doing it. There was a very famous one from India who, his name is escaping me at the moment, but he was a mathematical genius without having had any formal instruction in mathematics. He ended up at Cambridge, and one of the things that he came up with from his intuition was a formula, a very elegant little formula that could be used to compute the decimal expansion of pi, the ratio of the circumference to the diameter of the circle, right? Pi. And that ratio, he came up with a formula to compute it to billions and billions of places accurately, which of course he didn't do. We need a computer to spit out the numbers, but the computer never came up with such an elegant formulation. That was the human mind or the human brain. The computer can spit out the numbers faster than we can, but you could argue that human beings are still more intuitively clever in terms of being able to come up with formulae that predict in some accurate way what the computer will do if you ask it just to crunch the numbers. So we're on a kind of an equal footing, although on somewhat different grounds. But yeah, computers can do a lot of things faster than us. No question about that. I'm waiting for someone to come up with, detecting medical conditions. Jason, that's an interesting observation. And this is what we today call expert systems. So computers can crunch so much data at once that it's very often more powerful to get broad-based statistical analyses. So when computers are fed enormous amounts of data and then asked to compare, let's say, an X-ray or an MRI or some diagnostic measure with the data that's already stored, they can do a vastly greater amount of comparison in a much shorter time than a human doctor can. And so they can make a kind of detection or a kind of diagnosis based on vast amounts of number crunching or image crunching in a very short time. And it may end up being more reliable in some sense, although we always want to push back. Some of us probably want to think that there's something very special about being a human that a machine can never replace, and I hope that's so. But these kinds of expert systems are undoubtedly more powerful than any individual, just in the sense that they're able to crunch so much data in a short time that they can see things that an individual might miss. So I think that's right. There's a much more conspicuous way, however, in which computers have, navigation, Sudhanar, yeah, for sure. I think that most of us nowadays are not depending so much. If you set sail, you're not going to use a sextant, to try and figure out your your latitude. I think you're going to basically punch numbers into a computer and trust the machine to navigate for you. Pilots do this routinely on airplanes, and they're no longer looking at the stars or the sun or trying to figure out where they are on the basis of those visual cues. We have more sophisticated methods, but to keep everything up to date and on track, definitely computers are the tool of choice. What about chess? Surely you know that computers have, without question now, been able to beat the best chess players in the world. You know that Garry Kasparov was the unwilling victim of the first really powerful chess computer of that caliber, namely Deep Blue. Have any of you seen or heard about this? Have you followed this at all? Yeah, Jesse, you know about this? Okay. So it was thought for a long time that humans were never going to be beaten at chess, just because we're so frightfully clever, at least if we devote ourselves to that game. But that's not so. Because the Deep Blue program was able to learn. It's a learning machine. This is something Turing predicted. You see, toward the end of his reading, this is another mark of his genius, that he understood that machines could not be relied on simply to do what they're told to do, but that programs themselves, software itself, could be designed so as to enable a machine to learn from what it's doing, and therefore it could mimic a human even better, right? Because we're learning animals on a good day. And machines that are learning machines can therefore do things that we can do, and some of them better than us. So Deep Blue was the example of the chess program. Not the first version. Kasparov beat that, but it learned from its losses and eventually came back with, Deep Blue 2.0, and it defeated Kasparov. So the world chess champion is no longer a human. Or rather, human chess is relegated to a different league. You want to play in the League of Humans, you could be the human chess champion, but you're not going to beat the machine anymore. And then, more recently, much more recently, just within a few years ago, I think 2014 or 15, the same thing was achieved with Go. And Go, the Asian game of Go, it's called Go, G-O, much more complicated game than chess, way more complicated than chess in terms of its mathematical possibilities. It's played on chess is 8x8, right? You're playing on a 64 square board with 32 pieces initially, and then an ever diminishing number of pieces as they get captured. So the game becomes simpler and simpler in terms of the number of possibilities. Go is not like that. It's played on 19 by 19 board, so you have 381 intersections. The pieces are placed on the intersections, and they're all of equal value. There are black pieces and white pieces. They're stones that are placed on the intersections. And you're not trying to capture pieces, you're trying to surround territory. It's a much, much different kind of conceptual schema. And the mathematics are absolutely beyond what chess is in terms of possibilities. So it was thought that human Go players would remain supreme, but they haven't. A program called AlphaGo was built, and it also was a learning program. So it was able to play humans. It played itself first. It first played itself and learned, and then it started playing humans and learned, and eventually, not very many years ago, and to everybody's shock and horror, it defeated the world Go champion, a Japanese guy, and he just about was, ready to commit seppuku because this wasn't supposed to happen, and yet it did happen. So you can look at the movie AlphaGo. It's a documentary about how they developed the program. And the argument for learning machines is as follows, and AlphaGo is a great illustration. You see, the people who programmed Deep Blue were all chess masters. I mean, they knew how to play chess. They were great at playing chess. So they had a very good idea of how they wanted to devise the program to teach the machine chess and what kind of book learning, what kind of scenarios to put into the program, because they were all chess masters. So they had a really clear idea of where they were headed. But the people who built AlphaGo did not play Go. They only gave it the rules. They didn't teach it any strategy. They just said, okay, here are the rules. Play yourself 1,000,000 times and see how it goes. And then after it achieved a certain level, it started playing people and worked its way up, just like a heavyweight contender or any boxer. You work your way up the ranks. And this AlphaGo machine, it started working its way up the ranks and playing players of ever stronger caliber until it took on the world champion. And that was televised. And the movie documents all this. So Turing predicted all of that partly because he understood, for his day, brilliantly, the idea of a learning machine, although there was no such thing on the market at that time. He predicted that this is what would need to happen. So you have to give him credit about that. Did he predict anything about the exponentiality? Yeah, he didn't predict Moore's law, Jesse. He didn't predict anything quantitative, but qualitatively, yes. As we'll see momentarily, we're going to go to the reading, okay? So you'll see what Turing predicted. But basically, what's interesting is, at least for our purposes, is that although we have machines like expert systems, or agglomerations of machines, networks of machines, and although we have machines that perform very specific tasks, like playing certain games, or doing certain kinds of diagnoses, or indeed self-driving cars, that's a pretty specific set of tasks, driving a car. We have machines to do these very special things, or machines to calculate, trajectories of rockets, when they want to re-enter the atmosphere and so forth. We have a lot of very specialized machines. But what we don't have, and this is what's fascinating, we don't have a machine that can really fully pass a Turing test as he initially devised it. And a Turing test is really a much simpler thing. It's a more general conversation. So you could sit down with your friend and have lunch, and you could talk about current events, you could talk about sports, you could talk about, whatever, politics, you could talk about religion, you can talk about fashion, you can talk about whatever you want in a very general way and have an intelligible conversation without having planned it ahead of time, right? We all do this. But there isn't a computer that can sit down and have a general conversation with you yet. Not a very coherent one. And so that raises a really interesting question about Turing's prediction. Why don't we have a computer that can do exactly the most general kinds of things that Turing thought? And we'll give, in his reading, you'll see some examples of that. So this becomes now more deeply philosophical because we really don't know the answer to that question. Okay, so Sophie's asking, the game of Go was played by trial and error. Well, yes, it was. It was like a child. You give the rules of the game, and then they start playing, and they learn by trial and error what's a good strategy and what isn't. For a game like tic-tac-toe, it's very simple. You learn pretty quickly how never to lose. If you make the right move, you'll never lose. You might win, but the worst you can do is tie. And the computer learned by trial and error, playing itself, of course, very rapidly and a very, very large number of times. But then it started playing people, and it was able to learn from the games against humans as well, because it could record every move and remember every game. which is more difficult for us to do. So learning, but we are also learning animals, right? So back to this question. And remember, don't lose sight of Descartes' question, which is the question that animates all the readings in this section. What does it really mean to understand? Is that something the mind is really doing? You remember Descartes' example of the wax, right? So it's the mind. For Descartes, it's not the senses, it's the mind that's understanding things. So do computers really understand what they're doing is another question we could ask. Are computers just executing a program? Or do they actually understand that they are executing a program? And mostly not. You could say that the computer is able to execute a program and able to learn to execute the program perhaps better and better over time. But we are a little reluctant, are we not, to attribute to the computer the property that it understands what it's doing when it's doing this. And maybe when computers get good enough to do the kind of thing Turing envisioned, then they will at least be able to tell you they understand. So if you're talking to a quote-unquote intelligent computer and you say, well, do you understand that you're having a conversation with a person? And the computer's going to say, sure, I do. Well, is the computer telling the truth, or is it just programmed to say that? And could we tell the difference? Yeah, this is what we're going to tackle this week and next week. And there isn't an answer to this. There are a lot of opinions about it. In your opinion, Josephine, it's programmed. Well, and you're not alone. You're certainly not alone. And you could there would be a lot of evidence to support your position. For example, when Kasparov lost to Deep Blue, he was depressed. Like this guy was inconsolable because he had lost to a machine. When Deep Blue beat Kasparov, it didn't go out and celebrate that it had just become the world chess champion, right? The computer didn't say, okay, let's go out for a beer. Let's go out and celebrate. The computer, they just unplugged it and took it home. So you could say in that sense that the computer was doing something very well at an extremely high level, but had no awareness that it was doing that. So the computer, you would say, right, is you might be tempted to say it's just a machine and it has no awareness of what it's doing, whereas humans, you might want to say, not only do things, but we have this thing called awareness or understanding that we're doing it, right? You might want to say that. I certainly would want to say that, but then there's an answer to that, unfortunately. And then somebody like Turing is just going to come back at you and say, well, that's just because you're programmed to say you understand what you're doing, but that's just another kind of program. You're just running a more sophisticated program whereby you think you understand what you're doing. You see? So there are replies to those kinds of positions. We'll see. And I mean, the bottom line today is a robot called Sophia. And some of you may have seen her. And I urge you, if you just Google Sophia, the robot, I guess she's a robot. She's been, creepy, Jesse. Yeah, well, some people are definitely responding like this. There's this creepiness about her because she has a very humanoid voice. And she has facial expressions, and she's able to carry on. She could pass a Turing test, almost. She does get some help, though, because she's connected to a wireless network, and her programmers are able, at critical junctures, to feed her certain kinds of data, which will enable her to get over rough spots in a conversation. But she is, I'm saying she, it's a machine, but she is so impressive. She's built by Hanson Robotics. They spent a lot of time and money developing this. And she has emotions, or at least it looks like she does. She has facial expressions, so humans can relate to her. And you may or may not know that she was made an honorary citizen of Saudi Arabia after a demonstration there at a technology festival not that long ago. And you can see that online. I think I sent you a link to it in your Google Drive folders, that they did an interview with her in a live amphitheater full of investors. The whole thing was to raise money to continue the research. And she was so impressive, they raised a ton of money. And the Saudis were so impressed with her, they made her an honorary citizen. So there you go, okay, a robot. Pretty scary in a certain sense, but in another sense, it could be the future. All of you know this, and some of you have grown up with these technologies, so they're not surprising to you. But we're all living with computers on a regular basis. Computers are interfacing everything we do nowadays, are they not? And so you're going to see more and more, we're all going to see more and more robots, not just in the factories on assembly lines, but robots interacting with people. There are engineers across the street, well, I'm speaking figuratively about City College. I know engineers who are working on interfaces between digital chips and the human brain. So imagine if you could build an interface that would allow your brain to have a chip plugged in. So suppose you wanted to learn a language. If you want to learn a language, you have to, it takes a while, right? If you want to learn from the beginning, you've got to go through a lot of levels and a lot of practice and exercises and learn to pronounce things, vocabulary, grammar. I don't have to tell you. Many of you speak more than one language, and you know that once we learn a first language, we're off and running. But to acquire more languages takes effort, especially as we get older. But what if you could, I'm just hypothesizing, what if you could just say, okay, I want to learn German. All right, you get the chip and you plug in the chip and it interfaces with your brain and it uploads German. All of a sudden you're speaking German because you have the chip plugged in, or any other language, Japanese, Polish, whatever, any language you want to speak. Plug in the chip and you're off and running. Now that's a conceivable future too. So not around the corner tomorrow, but this is the kind of thing that inevitably will happen once we figure out how to interface the human brain with digital technologies. It's going to be amazing. So Terminator, sure, and also there's another movie with the Governator, Jason, as I like to call him. You remember when he was governor of California? They called him the Governator. But there's a movie called Total Recall you might want to see because it's based on that premise. All right, Total Recall. So let me ask you this, and this is a question that Descartes would certainly have liked the answer to because of his lack of trust in the senses. The premise of Total Recall is, or one of the basic early scenes in the movie, is that you imagine a travel agency, and for those of you who want a really low-cost vacation, you could go into the travel agency. Say you want to go to Hawaii for 2 weeks on a real low budget. Well, what you do is you go to this travel agency, and they plug the chip into your brain. They upload into your brain the memory of a 2-week vacation in Hawaii, and they put you in a tanning booth. Well, so you come out like you've been on the beach, right? And when you walk out of there, you really have the memory that you were in Hawaii for 2 weeks. You remember everything you ate. You remember the weather. You remember the, surfing or whatever you did there. And so what's the difference at the end of the day between you having been there and you having the memory that you were there? I mean, if you remember something totally vividly, then what's the difference between you having done the thing that you remember so vividly and just having the vivid memory? Is there any difference? Aside from the fact that in one case, you really did something, and in the other case, you only have the memory of having done it. But if you're just looking at the memory itself, I agree with you, Jeremy. At the end of the day, there is no difference, perhaps. If you have the memory of doing something, that's really the only evidence in the long run that you have, right, of having done it. Would you say the early stages of this virtue? Yeah, well, that's right, Jesse. I mean, I'm glad you're all thinking about this now, because this will, of course, that's a different conversation. But if we're talking about virtual reality, sure, virtual reality could, in a condensed way, give us false memories or give us memories of alternative realities. And this undoubtedly is going to start to manipulate what is, if there's anything that's natural about human memory and natural about consciousness, then computer-driven scenarios like virtual reality will be able to do very strange things with us and with our minds. And also scary things if you think about the possibilities of social and political control being exerted. If you think now about some totalitarian regime that wants to control people, there's obviously no more powerful way to control people than controlling their minds, right? And that would be way beyond just propaganda, to which we're all vulnerable anyway, actually controlling us with virtual memory and virtual realities would be certainly a scary thought, but to a certain extent, it's already, in a sense, happening. So these are all questions that are raised, from this very basic question of Turing's, can a machine think? And if a machine can think, then can it outthink us? And then if it fell into the wrong hands, then to what diabolical purposes might it be employed? This gives rise to science fiction and political dystopia and a lot of other possibilities. It also gives rise to of course, to benevolent scenarios. It's not all the stuff of nightmares, but it certainly is food for thought. And the possibility that you are obviously considering in this, what I see from your feedback, is you're really beginning to realize that this technology is more powerful than anything we've ever invented. It's not like bicycles. It's not like internal combustion engines. It's not like, those things. It's something that really rivals our own abilities to mentate, that is, to use our minds. So let's look at Turing and now see, with perhaps this benefit of hindsight, just exactly how prescient he was in foreseeing so much of these possibilities. But bear in mind, if you're trying to still find consolation in being human, and that if you're still thinking that, well, but humans are, we built the machines and machines didn't build us, then you can find that, because there still isn't a computer that can have the basic conversation outside of Sophia, I guess, that Turing envisioned 70 years ago. All right, so let's have a look at Turing. Let me share the reading with you. Bear with me while I pull this up. This is in your text, and you can find it online. It's a very famous reading, Can a Machine Think? Published in a journal called Mind. You see, interestingly, he did publish this in a philosophy journal, not in a journal of technology or a journal of engineering. He published it in a philosophy journal, and so it's had a huge impact over the years. It's one of the most famous papers ever published in this sphere. And you could say it really launched AI. Fair to say it was one of the main publications that got people thinking about this field back then. So, okay, I'm still looking for the screen share. Here it is. And bear with me. Are you able to see the reading? Could someone say yes, if so?
Yes.
Okay, thank you. All right, so can a machine think? Well, a little bit about Turing here, and a little biography of him. But basically, he's going to propose this thing called the Imitation Game, and that's why Hollywood chose that as the title of the movie, just because it's very well known. As I say, we also call it a Turing test. But his word for it, he was modest. He didn't name it after himself. That came later. He called it the Imitation Game. So, can a machine think? And again, you see, if you read Turing carefully, this is very easy to read. It's ordinary. He's speaking in ordinary language. There's no jargon or terminology here outside of ordinary language. But he thinks that the question itself is not a good question, because we don't know what thinking is, precisely because of the debate between Descartes and later on Berkeley and later on Churchland. Since we don't really know what thinking is, it's only going to complicate the matter if we ask if a machine can think without really knowing what it means to think. So Turing asks the question to kind of attract our interest, but then he reframes it in a very useful way by saying that, well, we could tell indirectly if a machine could think, if it could pass the imitation game. So we don't have to know what thinking is to answer the question. We have to know whether or not a machine can effectively play the imitation game. So that's the way he dodges the really difficult ontology of thought and goes into this functional question. All right, I'm hoping you're seeing or beginning to see the connection now. If we can build a machine that appears to have attained the function of thinking and conversation, then we don't need to know what thinking is in order to have achieved the functionalist goal. So here's a hypothetical conversation that he would like us to be able to have with a machine. I've highlighted it in yellow. And remember, this is not possible even today, not in its entirety, and not even, maybe with Sophia, again, she could maybe do this, but I don't know of any computer you can go and buy, online that could do this. So you're the interrogator, you're asking the questions, okay? And you're trying to ascertain, remember, in the imitation game, you, the interrogator who's asking questions, is trying to tell whether you're talking to a machine or a person, okay? And here's a typical set of questions you might want to ask. So the first question is, please write me a sonnet on the subject of the Forth Bridge. This is a bit of British geography. The Forth Bridge is not a number, it's a name, and it's a bridge that connects England to Scotland, okay? It's in the north, and so it runs over that river. Please write me a sonnet on the subject of the Forth Bridge. Well, the answer comes back, count me out on this one. I never could write poetry. Well, a lot of us would say that, right, if asked to write a sonnet, but a machine might say that as a way of dodging having to write a poem, right? So you wouldn't really know if you were talking to a person or a machine. Next question, add these two 5-digit numbers. Okay, the answer is pause about 30 seconds and then give the correct sum. Okay, why is there a pause of 30 seconds? Anybody? Speak up if you want to activate your mic. Why is there a pause of 30 seconds between the question and the answer?
So there's time to actually find the correct answer, since a machine could automatically do it.
Yes, and so you would know if the machine came back too quickly with the right answer, you'd know it was the machine, because a person is going to take a few seconds to add up those two numbers, correct? Or at least a person's going to take a few seconds to cheat and punch the numbers into their calculator while they're talking to you. But in either case, it's going to take a few seconds, whereas the machine could spit that out immediately, and then you know it was the machine. So the programmer would know to put in a pause, so you, the interrogator, would still not be sure if you were talking to the person or the machine, correct? So that's why there's a pause. Okay, next question. Do you play chess? Well, the machine says yes, the person says yes. So you give it a very simple chess problem with only 3 pieces on the board. It's a 1-move checkmate. Every elementary chess player could do this. It's a very easy problem to solve. Again, a 15-second pause to visualize or to set up the chessboard, and then you see immediately that there's a checkmate there in 1 move. So both the machine and the human could do that. So confronted with this if you're texting this, getting responses by text, you wouldn't know if you were talking to a person or a machine. Or at least if you didn't know, then that machine would pass the Turing test because you couldn't be sure. So that's what Turing envisions as a kind of imitation game. If we had a machine that could do this kind of thing, you really wouldn't know whether it was a person or not. And similarly, there's a variation of the game that he introduces earlier in section 1, where you're talking to 2 entities and you're trying to ascertain which is a man and which is a woman. So once again, you could have answers coming back that would make it completely unclear as to who is who, or you could have a machine trying to imitate a man or a woman and would give you answers such that just by asking questions you wouldn't be sure if you were talking to a real woman or again a machine, or in today's case a robot like Sophia, who would give you those same answers probably that a real person would give, and you really would have a tough time with a set of basic questions like this, knowing who you were talking to, a person or a machine. So he then goes on to describe the function. This is a bit more technical, and you don't need to understand the logic, but he's describing what goes on inside a digital computer when it's basically computing. And that's where he segues slightly into the model of the universal Turing machine, okay? By explaining that the machine is in a certain state, and it takes input, and then based on its internal state, combined with the input, the internal state also includes the program that it's running. So the instruction that it's supposed to follow is part of its internal state. And when it gets input, it follows whatever instruction it's supposed to follow. And that combined with the input will produce what we call an output. And that will be the answer to the question or whatever it is the computer's trying to do, or the next move of a game, or if it's driving, is it supposed to hit the brakes or the gas or whatever. But all of those things can be described very precisely in terms of a digital machine. So you have input, an internal state, and an output. And that's a diagram that just shows it. This, again, is that other thing that Turing is famous for, the universality of digital computers, because it doesn't matter how complex they are or powerful, or whether you're using a parallel processor or whether you're using one of the earlier kinds of machines that are very cumbersome and complicated and not very efficient, but they all work on the same conceptual model, and that's really this thing, this diagram: input and internal state, and then the output that follows. They all work this way. And I could show you a whole series of photos, or you can look online, of the different technologies. So those of you who were born fairly recently, whether you're millennials or a little bit older than that, you're all born into the world of computers, with a few exceptions. I am not. I like to say I was born BC, okay, meaning before computers. So we were born before computers, and we saw them come into the world. So the first generation, and you'll never have to worry about this, but one of the very first computers that was built was called ENIAC, ENIAC, and it was built, I believe, by IBM in the U.S., and it used something that you would not know the name of today. If I say that it used vacuum tubes, I'm betting that almost none of you know what a vacuum tube is. I'll stop the share for a second. A vacuum tube is what used to be in old TVs. A cathode ray tube is another name for part of it. And again, you don't know what I'm talking about because you were all born after computers, AC. I was born BC, so I know these things. But a vacuum tube is literally the precursor of a transistor. Arsh, you know this. Good for you. So Arsh knows this as switches. That's correct, Arsh. So a transistor was a huge development, came about in the 1950s. And in fact, there's an American who won 2 Nobel Prizes. Shockley built the first transistor, and this was a huge development. But there's only one thing we still use vacuum tubes for, and some of you, I hope, will be amused. So I'm going to tell you this, that if you like rock music, and I used to, back in the day, I played rock music, and the amplifiers used to use vacuum tubes. If you look at movies of Woodstock, if you look at movies of Jimi Hendrix or Eric Clapton or these guitarists who played lead guitar through big amplifiers, those amplifiers were all using vacuum tubes, not transistors. And they used them deliberately because when the vacuum tube heats up, it distorts. And if you like feedback and you like distortion and you like the rock sounds, then you want vacuum tubes so you get those cool rock sounds. But if you're going to use vacuum tubes for computing, you don't want distortion, because distortion means the output's distorted and you're going to get the wrong answer. So that's not such a good thing when you're computing, right? You don't want the wrong answer, especially in the 60s when they're computing the trajectory of the Apollo missions and they need to calculate the re-entry, and there's a very narrow window in which the rocket's going to re-enter the Earth's atmosphere. If it comes in too shallow, you know this, right? If the rocket comes in too shallow, it literally bounces off the atmosphere like a rock skipping off the water, and it goes into space, doesn't come back. Or if it comes in too deep, too steeply, it burns up from the friction. So the actual survival angle for re-entry is quite narrow, and you certainly don't want your computers overheating and distorting the output when they're doing that computation. Actually, they didn't do it on computers, they did it on slide rules, which is an analog device. Okay, So the transistor solved that problem because it was much more efficient, much more powerful, and it did not distort. So they were able then to build the next generation of computers using transistors. And radios, we had transistor radios. They were very powerful and very compact. And now they figured out how to put millions of transistors on a tiny wafer the size of a postage stamp. And that's one of the reasons why computing got more powerful, because the transistors themselves could be miniaturized and layered. Whereas in the old days, right up to the 80s, a transistor was a thing you could hold in your hand. Literally, you could solder it to a motherboard. I used to build them. And these discrete components were actually visible, and you could hold one and actually put it into position. Nowadays, they're doing everything with a much, much more advanced 5th, 6th generation technology, so you don't hold a transistor in your hand. You hold a wafer, which has millions and millions of transistors built into it. So that's where the technology has gone. That's why it's much more powerful. Okay? So just, to remind you of how far we've advanced in a very short time. Now, there's one more point that we're going to look again at the reading to illustrate something. Some of you may think, and may have good reason to think, that computers are so powerful that sort of anything is computable, but it's not the case now that everything is computable, even though we have all these expert systems. Can someone give a quick example of something that's still not very predictable? Does anything spring to mind? I'll give you a hint. Look out the window. Does anything spring to mind that's not 100% predictable or not even close? Right. Maybe I gave you too big hint. Oh, emotions, Susanna. Yeah, but you don't get those looking out the window. I hope. I mean, that's another story. But the weather is it's right, Jeremy and Luis. I was thinking about the weather, and there's a very good reason why the weather's not predictable. You see, this now is going to make us think a little more deeply about how we actually operate and how machines operate. There are very small differences in the parameters that we feed into an equation, or the metrics as they're today called. Very, very small differences in the data that you feed into a program could, in some cases, produce huge differences in the output. That's actually called chaos. That's the basis of, or one simple way to understand chaos theory, that a slight difference at the beginning of a process can end up making an enormous difference or enormous divergence at the end of a process, and that divergence is not predictable because of very, very small perturbations that occur throughout and add up and cumulatively end up dispersing things in such a way that although they are deterministic, they're not predictable. So that's very interesting. The analogy would be, to understand this in a physical way, suppose you were a skier, and suppose you want to ski down a mountain, as many people do. So you take a helicopter to the top of the mountain, and you ski down the mountain, okay? And you get to the base. All right. Now you take the helicopter back up to the top, and this time you ski down the mountain, but you're diverging only a couple of degrees. Say you went down, this direction the first time. The next time you just diverge very slightly, and you maybe 1 or 2 degrees to your left, and you ski from there. But when you get to the base of the mountain, you could be miles and miles away from where you were last time, correct? You get this? So a very small divergence at the beginning of a process, very tiny, maybe even negligible, could end up in a huge divergence at the end of the process. So this is why the weather is not predictable, because as good as our models are, they're only as good as the data that's being fed into them, and it's impossible physically for us to gather enough real-time data to be able to feed enough into the computer for its predictions to be accurate. So we can track hurricanes to an extent, but we still can't be sure where they're going to make landfall because of the internal perturbations that we're not tracking. And so those small variations that are taking place within a hurricane could lead to a large deviation in its trajectory. Similarly, a snowflake that falls from a cloud it's totally determined where that snowflake's going to land, but it's impossible for us to compute because at every position of that snowflake's descent, there are wind currents and changes in humidity and changes in temperature and changes in the shape of the snowflake itself, which affects the way it drifts through the air. And so there are all these millions and millions of data points that we simply can't feed into a program. And that's why we can't predict exactly how much snow is going to fall. That's why they tell you between 2 and 5 inches, and sometimes it's a foot, because they're totally wrong. It's not that the machines are faulty. They're only as good as the input. The output's only as good as the input. And the input could never be as accurate as what's going on in nature, because we simply don't have the instrumentation to be able to mirror that input as accurately as we would like. Okay? So the machines are powerful, but they're still only as good as the input. And then if you think about us, I see some of you, Ron, Susanna, okay, emotions, dreams. Yeah, they're not predictable either, probably for a similar or a parallel set of reasons. Because our emotions, Susanna, they depend on a whole bunch of things. And, there's the input that maybe gives the emotion or makes it arise, but then there's the internal state, like a computer, and we have all these neurochemical transmitters and different concentrations of them in the brain, and all these different hormones and different things that are going to be triggered, and our bodies are going to do things similar to the weather. They're so complex that we can't possibly track everything that's going on internally, and that's partly why people are unpredictable too. Very largely. Sometimes that's a good thing, sometimes not so good. But we simply can't predict what people will do for these similar reasons. So could AI ever be that random? Well, Jesse, this is the thing. It's not random. Please use the word carefully. Random is a very different meaning. I'm saying that the processes that we're describing are actually deterministic. It's just that we're not capable of computing them, right? Unpredictable, yes, but that's the point, that this is the real key takeaway, right, or a key takeaway, that something that is deterministic is still not necessarily predictable, okay? And something that appears random might actually be deterministic. Researchers used to be able, not that many years ago, to go out and buy a book of random numbers. Now, you can probably get it online. I'm sure they have a digital copy. So what do you need books of random numbers for? Well, for different kinds of inputs, you might want random numbers. The interesting thing is that these random numbers are not random. The pseudo-random series that you could buy if you need random numbers to plug into an experiment are generated by a computer. All of your computers at home can generate random numbers. There are little programs easily programmed, to generate random numbers, as many as you want, but they're not random. They're deterministic, but they have the properties of random sequences. So there are also completely deterministic things that, if analyzed from a certain perspective, appear random. So the world is always a little bit stranger. Well, so like the lottery, well, Sudhir, I don't know, is that a conspiracy theory? I guess if the numbers are generated by a computer, if the winning numbers in a lottery are computer generated, then absolutely they're not random. But they certainly have the properties of random numbers. Otherwise, we would be accusing the lotteries of being fixed. And since we assume they're not fixed, they're not rigged, then they must be random. But if they're being generated by machines, then they're not random. So, okay, I'm glad you're thinking now about these things. So is this a lack of free will? Well, that's another great question, Susanna. I mean, is there free will or not? We think we have it. But then again, it might be one of these deterministic processes that looks like it's free, or it looks like it's freer than it is. All right, I want to come back to Turing, but just to tie this in with what Turing was saying. So a couple of developments that occurred not long after Turing, but in the early 70s, when languages got more sophisticated. Programming languages got more sophisticated. So there was a big attempt then to build programs that could pass a Turing test. And I want to tell you about two of the stellar attempts. And you can find them online, and you can play with them. And one of them is called ELIZA. Okay? This was a 1970s attempt. So ELIZA is a program built to imitate a psychotherapist. So ELIZA is a machine, but she sits there, or it sits there, and it says, "So how are you feeling today?" And you start talking to Eliza. You text your input. Eliza takes the input and will ask you more questions based slightly on your input and based slightly on things that are pre-programmed. So Eliza will have a kind of a conversation with you. And if you Google Eliza, the psychotherapist, I know that there are interactive online versions now where you can actually you can get a free psychotherapy session with Eliza. So you might want to ask, well, did Eliza put psychotherapy out of business? Not in the least. Why? Because after about 2 minutes of talking to Eliza, you realize it's a machine. Because it's not capable of conversing in a psychotherapeutic way as nearly as well as a person. So Eliza fails the Turing test, in other words. Eliza is not really very good at the imitation game, because if you talk to her for a few minutes, you'll know immediately you're talking to a machine. It gets very circular. The ability of Eliza to question is very narrow, and the ability of Eliza to take in a variety of input and have a meaningful conversation based on that is not very good. So you'll see it's an early attempt to get a computer to pass a Turing test pretending it's a psychotherapist, but it's a failed attempt, so it's very instructive. We often learn more from failure than from success, right? So you can look at her as an example, or it as an example of an early attempt to do what Turing wanted. And there's another one that was more successful, and it's very amusing. Its name is Parry. And Parry is a program that imitates a paranoid personality. So this is why it's called Parry. It's a play on the word. So this paranoid program tells you a story. If you say, so, how are you today? And it says, I'm really scared because they're after me. And if you say, who's after you? You say, the mafia, they're trying to hit me. They got a contract out on me. They're trying to hit me. And then you say, well, how do you know this? And it says, well, I just know, there are signs, I've been warned. And then you say, well, can't you go to the police for, to get protection? You say, oh, I can't trust the police. So it's totally paranoid about everything. And it's pretending to be a kind of paranoid personality type. So the guy who programmed this basically printed a transcript of a typical conversation with Parry, and he bundled that with a bunch of other real transcripts of psychiatrists talking to paranoid personality types. They were interviewed at intake. These people were taken to an emergency room, were taken to mental hospital, and they were given an initial briefing or initial session with a psychiatrist who recorded their conversations. And so what they did was they sent these transcripts of Parry, which is obviously a simulation, right? Another word for this, a simulation of a conversation with a paranoid, and some real transcripts of actual conversations between paranoids and psychiatrists. And they sent a bunch of transcripts to a bunch of psychiatrists and said, can you pick out the one that was machine generated? And they could not pick out that one with any degree of accuracy more than random. So therefore, that machine passed a Turing test. You could say it passed a Turing test, because even a bunch of experts could not tell whether the real conversations or the simulated conversation had any significant difference between them. Okay? So this looks like a complicated question. What if we are also just information? Well, that's what Turing was kind of hinting that maybe we are. We humans are just very, very complicated, sophisticated kinds of storage machines. And if that's the case, then the functionalists like Turing is going to say, so the human brain is an amazing development evolutionarily, totally incredible that we can do all the things that we can do. But it's not the be-all and end-all, because we could build an equivalent based on a totally different structure, right? In this case, digital computing and TTL architecture. And we could, based on that structure, come up with a function which is just as good and just as interesting as a human being. So what do we call creativity? These are all really good questions, Arsh. And is there a test for that? Yes, there are. And so, I mean, now I'm really glad you're asking these questions. Obviously, this is an intriguing topic for us, and it's made more relevant by contemporary developments. If Turing could come back, he might give us another paper, to answer his first paper, but we have to answer for him. What is creativity? Well, it turns out that nobody knows what creativity is, and there are a lot of attempted explanations, and others. But let's put it this way, that one of the things that machines still don't do as well as people, although they play chess better than us and go better than us, and do other expert tasks maybe better than us, but they certainly don't write poetry better than us, they don't write novels better than us, and they don't write music better than us. And if you listen, you can listen. There's a lot of computer-generated music out there. Humans are still better at it. What about imagination? Well, Ron, we're having this conversation, which is not pre-planned. I mean, I pointed to a reading, we've discussed it, but in a totally not planned way. So this whole conversation today that we're having and all the things people are coming up with spontaneously is kind of, imagined, right? It wasn't preconceived. So in a certain sense, it's spontaneous, right? Imagination is spontaneous, we think. And it's not the case that any computer is teaching this course. We don't have a computer teaching a course on Turing, although we might build a program that could. So as long as we humans are doing this, then there's some hope that we're still better than the machines in some sense, and maybe it is imagination that enables us to do that. But what is imagination? Again, no one can really say. What Turing would say to you, Ron, an answer is that Turing would say, well, if we can build a machine, that can function as well as the human imagination, we don't have to know what imagination is, but if we get a computer that could write a novel as well as Tolstoy, or a computer that could write a symphony as well as Beethoven, or a computer that could write poetry on the spot, or maybe spontaneously rap, as well as a rap artist, then we would say, well, that passes the Turing test, but we haven't done that yet. So maybe we're still a little bit special. It doesn't contradict them, Arsh. It just avoids the hard question about the ontology, right? It's not contradicting Descartes. It's just saying if Descartes says, I think, therefore I am, then we can build a machine that does this functionally without having to know what thinking is, right? If we can build a machine that says, I think, therefore I am, then that machine functionally, it might be just as good a philosopher as Descartes was. If we build a machine that can say, to you that the universe is made of stuff, just like me, the machine, and just like you, the biological machine, then maybe we could build a machine that's programmed to be an eliminative materialist, and maybe it could even do as good a job as Churchland at defending eliminative materialism. So he's not contradicting Descartes and Churchland. He's saying, Turing is saying, that machines actually should one day be able to do the same things that Descartes and Churchland do. In which case, functionally, obviously they're able to philosophize, right? I'm not too worried yet about that. If I were a chess player, I'd certainly now know I could never be the world champion. But as a philosopher, I'm still safe for a little while because the robot Sophia is nowhere near being a philosophy professor, although maybe next year she will be, and then I can retire. But Turing is not contradicting philosophers. He's taking this functionalist tack and saying what we really need to do is learn how to build a machine, learn how to build a computer that can philosophize. And then we'll have succeeded at doing something really interesting. So what we're going to do Thursday in my breakout group, and I hope you will continue in your breakout groups with your instructors, is to look at, once again, the objections that Turing raises to his own thesis. And the second part, or the remaining part of the Turing reading, which I hope you'll all do, on your own time or have done it already, is once again this very useful exercise. He raises a lot of objections. The reading in your textbook only gives you about 6 or 8 of them. He raised more than that. But it gives you the most interesting ones that some of you already have raised today in your own words. And Turing in 1950 raised all the standard objections that people are still raising and was able to answer them well enough. And I want you to look at that, and we'll look at this on Thursday. Okay? But that segues into next week, which is Searle. And John Searle, who's a contemporary philosopher, comes up with, if there is a decisive argument against Turing, it is this, that even if we can functionally build machines to do all these things, that humans do, John Searle believes, and many are with him, that machines still don't understand what they're doing. They're just running a program. Whereas we, humans, actually are running some programs, maybe like machines are, but we also understand things. And this property of understanding is a distinct human property, and it's not reducible to a program. So in other words, you can write a program for your computer to do different things, but you can't write a program for it to understand. Nor can we explain what understanding is. So that's the more interesting point that's been raised to refute, in a sense, Turing's functionalism, that understanding is something we can't simulate. Or rather, we can simulate it, but it's not the real thing, and it'll never pass a Turing test. Okay? So, is there anything random possible? Well, that's a very deep question, and I'm going to totally dodge it because it's about philosophy of mathematics and logic more than philosophy of computing. So it's a wonderful question, and hang on to it, or meet me in an office hour and we can just look at that. Okay, so we're pretty much done today. I hope this has been helpful or useful in understanding what computers do and what maybe they don't do, and in giving you some more food for thought on this topic about, what's a mind, what is a brain, and now we've added to the mix, what is a computer. Okay, so I look forward to seeing those of you in Section M on Thursday, and I hope you'll continue to read the end of that paper by Turing, look at the objections that he raises, which were made by contemporaries and made historically by others who anticipated him, and look at his answers. He does a great job. Okay, and if you want to watch the movie, it certainly would be interesting for you. The Imitation Game is something you can see between now and then. All right, you're very welcome, everyone. Elizabeth and Ashanti and Sudamar, all of you. Anastasia, you're all very welcome. Have a wonderful day, a wonderful week. I'll see some of you Thursday. And then next week we'll look at probably the most decisive argument against Turing that anyone's come up with. It's called the Chinese Room. It's a very interesting allegory, okay? So we're almost there at the end of part 1 of this course. All right, be well, everybody. I'll see some of you on Thursday and everyone else next Monday, same time, same station. Take care and bye for now.